Swayam Prabha. Digital India. Educated India.
Yeah, welcome back. So, today we will take up a bit about the sinusoids analysis. Last class we have actually seen that the synchronous generators, as they are called, or alternators as they are called, basically generate three-phase supply, which can be written as, in time domain, can be written as, actually this I will just not write this phi for convenience. First one I will just write it as sine of omega t. Vb will be sine of omega t minus 120 degrees or 2 pi by 3, and Vc of t will be Vm sine of omega t minus 120 degrees. Suppose if this voltage was sine of omega t minus, let us say, plus phi, then automatically all the three phase voltages are shifted by an phi angle. So, therefore, all of them will be I will have to add the 240 degrees. Yeah. So, it will become Va of t will become Vm sine of omega t plus phi, Vb of t will become Vm sine of omega t plus phi minus 120, and Vc of t will become Vm of sine of omega t plus phi minus 240 degrees. So, therefore, it is better to just keep it simple. This is not really any impediment in generalization, and we can generalize it any time later. So, we can write like this, the three voltage waveforms. If you want to write it as cosine, if this one you take as cosine, it is equally fine if you write these three as cos of Vm cos of omega t, Vm cos of omega t minus 120 degree, and Vm cos of omega t minus 240 degrees. So, out of just convenience for me, I am going to write this as sine of omega t minus 120 degree and sine of omega t minus 240 degree. Now, this is generated from a alternator or a generator, because the three windings are symmetrical with respect to each other, exactly identical, only displaced 120 degrees in space, having equal number of turns, and they see exactly the same magnet rotating in exactly the same way, because the air gap configurations are not changing. So, therefore, each one of them is generating the same peak amplitude Vm, and they are displaced symmetrically by 0, 120 and 240 degrees. So, such a supply will be called as a balanced supply. Such a supply will be called as a balanced supply, and remember that a synchronous machine or a alternator by its very construction generates a balanced supply, a three phase balanced supply. Now, to jump a bit forward, I will be showing to you later on that in this class that these can be shown as three vectors, and these three vectors are actually called as phasors, and their value is this Vm, and so this is the phasor for Va, this is the phasor for Vb, and this is the phasor for Vc. They are equal in length and 120 degree apart. They are vectors basically, but because we are doing with three phases, these vectors are called as phasors. But indeed actually what just we mean is that they are just three vectors equal in magnitude displaced 120 degrees in phase. This is fine. We will why this is done, you will see as we proceed. Omega, as I told you, all of them have to have the same frequency, which is happening because of the construction of the machine, which in India is going to be 100 pi radians per second. Now today the one question which I am going to answer is, suppose I have a RLC circuit, a series RLC circuit like this, and I have a series RLC circuit like this, and I have a switch, and I have this, I am sorry, I have a switch, and let us say I close that switch at t equal to 0. This supply is Vm sine of omega t, and this carries a current I, this resistance is R, L and C. So, the question is, what is I of t? This is the first question that I want to answer. I will make my question a bit more precise. I will ask the question, what is the steady state nature of I of t? By this what I mean is, when I close a switch like this, and you have seen it in your basic differential equations, calculus of basic differential equations, what I know is any response will have, so if this is I of t and I am looking at its response, it is basically summation of two things. One is a transient response, I transient of t, let us say, and a steady state component of t. Now, a transient response I am not interested in going right now, but with a second order RLC circuit like this would appear, it is not come out very symmetric, but it will be symmetric like this. Basically you will see that if there are some initial charges, or if there are some initial charges, for example in the capacitor or whatever, it will cause some current to circulate, but because of the dissipative element R, over a period of time this component will die down and go to 0. This is a part of our dissipative systems, because most of the engineering systems that we are dealing with are dissipative systems. If let us write this differential equation and it will be very clear to you. The first component is R of I. So I am going to write basically V of t to be equal to voltage drop across this VR plus VL plus VC. VC plus minus this is VL and this is plus minus VR. So this is my This is the voltage, and each of them is actually a function of t. I am not writing it right now, but it is clear that each one of them is a function of t. Now, for Vr of t is the r times of I. VL of t is nothing but L di by dt, this also we know, and Vc of t is the charge on the capacitor divided by its capacitance, but the charge on the capacitor can be at time t is like looking at the current, integrating the current, because I is dq by dt. So, to get the charge we should integrate the current from minus infinity to t, and this is a dummy variable I tau t tau. So, this will give you exactly the charge, and at minus infinity you can assume that the capacitor was discharged, and so this will give you the charge at the time t, which you divide by c, then you will get the Vc of t. So, therefore, the equation for, and all of them are carrying, because it is a series circuit, all of them are carrying basically the same current. So, you can write this as V of t. The voltage drop across the three, carrying each of them carrying the same current I, being a series circuit, is equal to the voltage which is applied, which is Vm sin of omega of t. Now, if you take one more this is called as a integro differential equation. Incidentally, this is called as a integro differential equation, and if you want to get a differential equation out of it, you just take one more times derivative of it, so that this becomes and you know that if V equal to Vm sin of omega of t, then dV by dt will be equal to Vm cos of omega Vm cos of omega of t. So, this can be written as, write this as L d square I by dt square plus R di by dt plus I by c can be written as Vm cos of omega Vm cos of omega of t plus a harmless 0. Now, because this is a linear circuit, you could think of it as solution to this, a generic solution to this you could consider it as the steady state component called current, and a specific solution to this you could consider it as the transient, you could consider it as a transient response. Now, this transient response will come into picture if in this circuit this transient response will come into picture if only this capacitor has some charge on it. Otherwise, this circuit will not have any transient response, because the switch is open till t equal to 0. So, this cannot carry any current, and so only possibility is of this having a voltage. So, if I just close the switch without applying this Vm sin omega t, then this voltage which is across the switch will drive a current which will keep oscillating, and as a consequence of it, this stored voltage in the capacitor will be partly transferred to inductor and partly dissipated, and some kind of a exchange of these are the two energy storage elements, and this is a dissipative element. If I do not have any of this and just close this, then over a period of time what is going to happen is this whatever initial charge, half whatever initial energy which is there stored on it initially at the V0 minus, whatever was the voltage across the capacitor which is stored there, this energy in the capacitor will gradually be dissipated in this resistance. So, this is what is going to happen. So, once this energy gets dissipated, it will gradually go to 0. Theoretically it will go to 0 at infinite time, but practically after a few constant few time constants or few constants, after that this could be neglected and we will be left with only the steady state response. So, this is that transient response of, this is what I was talking of as the transient response which will die over a period of time. And if you for this you just have to solve this, it is also called as the natural response. So, you just have to solve this second order differential equation, the homogeneous second order differential equation, and get a solution for it, and then based upon the initial conditions on the initial inductor current and the capacitor voltage, these are the two energy storage elements which are associated with differential equation to begin with. Once we know their initial condition, we can actually find out the transient or the natural response of this circuit, but it will decay with time. So, right now today I am not going to worry about the this particular problem, the response of the natural response. So, I will assume that natural response has died out, and because steady state response basically we are looking at t tending to infinity, what is happening to this. So, I am only interested right now in this particular part, and so we will just not bother about the transient response. So, then I will come back to this integral differential equation, the starting point that we had. I will take this integral differential equation, and to get steady state response of I of t. So, to get the steady state response, I am not going to use again and again ISS as my subscript. I will just say that I will probably just use IS of t maybe one time, and I will just say, let me hypothesize that if this is sinusoid, what is, I will write this as Vm sin of omega t. Let me hypothesize that this is some Im sin of omega t plus phi. This is a hypothesis. This is an assumption I am going to assume. Now, let me check if this works out. There is a reason for making this assumption. The right hand side is a sine function. So, I know that if I take a derivative of a sinusoid, I will just take say sin omega t, it is going to be omega cos of omega t. So, it is a cosinusoid, basically in other words like a sinusoid only, same shape is preserved. Sine and cosine have the same shape, only thing is that t equal to 0, one is at 0, another is at its peak, but the shape is really not different. So, both the waveforms have same shape, but this one is just scaled by an omega. So, the frequency also has not undergone any change. it is still cos of omega of t. Similarly, if I integrate sine of omega of t, then I can write it as 1 by omega minus of cos of omega of t. Why? Because when I take differentiate cos of omega of t, it will be omega minus sine of omega of t, and that minus minus will make this minus minus will make it plus, omega will cancel, and I will get this thing. So, integrating also a sine or a cosine basically again creates the same shape, but this time it is scaled down by omega. When you differentiate, it is scaled up by omega. So, therefore, the idea is that okay, sinusoid is a good idea here, because sinusoids preserve sines and cosines. At the end of the day, I have something on the right hand side. So, I want to see if this works out properly for me. So, let me now with this motivation, let me start with the assumption that let us check if this hypothesis works out. This has two unknowns Im and phi, and I am assuming that the steady state waveform is Im sine of omega t plus phi, and let me see if it works out. So, best way to see if it works out is to substitute this in this equation and then equate it with Vm sine of omega t, and then try to see if Im and phi can be fixed to appropriate values. If that happens, our job is done. So, the first term will become Rim sine of omega t plus phi, plus the second term will become omega L Im cos of omega t plus phi, plus the third term will become 1 by omega c minus of cos of omega t plus phi. This is the LHS. RHS is fixed to Vm sine of omega t. So, now let us try to write this as Rim sine of omega t plus phi, and I am going to take cos of omega t plus phi common here. So, I can write this as omega L minus omega c Im cos of omega t plus phi, and so I am take Im common here, and I will get this as r sine of omega t plus phi plus omega L minus omega c cos of omega t plus phi. Now, this is what I am going to do is, I will, let us say this is r, let us say this is omega L minus 1 by omega c, and let us say this is theta. Now, consider this vector which is of length say z, it is called as impedance. We will come to that a bit later on, but in this right angled triangle, this hypotenuse which is of length z, the impedance can be written as this. So, now I am going to divide this by z and multiply also this by z here. Now, r by z, so now r by z can be written as cos of theta. So, I will first write the first term as sine of omega t plus phi, and r by z I will write it as cos of theta, plus I will write cos of omega t plus phi first, and this omega L minus omega c divided by z, this is the sine of theta. So, I will write this as sine of theta, and now you can see that this is of the type sin A cos B plus cos A sin B, which is nothing but sin of A plus B. So, I can write this as sin of omega t plus phi plus theta. So, the LHS has simplified and it says that yes, it is going to be a sinusoid only, nothing to worry about. We still got a sinusoid, and now our RHS is Vm sin of omega t. So, and the LHS and RHS should be same. So, therefore, Im times of Z should be equal to Vm. In other words, the peak amplitude of the current should be equal to Vm by Z, and this is sin of omega t. So, therefore, phi plus theta should be 0. So, therefore, the phi plus theta should be 0, or in other words, phi should be equal to minus theta. This is a constant of the circuit. So, this is a circuit constant. Why is it a circuit constant? Because tan of theta is omega L minus 1 by omega C by R. So, once you have fixed L, C and R and omega, which is anywhere at the 50 hertz supply, then tan theta gets fixed, and the phi will become equal to minus of theta. So, with this what I have just 1 minute, LHS sin of omega t plus phi, yes. So, I of t, which is equal to Im, which in our assumption was Im sin of omega t plus phi, will become equal to Vm by modulus of Z, the impedance times this phi is nothing but minus of theta. So, therefore, sin of omega t minus of theta. So, the current is also a sinusoid, scaled, the peak voltage has to be scaled by the magnitude of the impedance. So, it has to be scaled by the magnitude of the impedance Z, and lags the voltage waveform Vm of sin of omega t by an angle of theta, radians or degrees, as it would be expressed, and of course, this is in amperes. So, sinusoid at the same frequency, remember this very clearly now. If you give a sinusoidal excitation to a RLC circuit, a series RLC circuit, the response, the steady state response is also going to be sinusoid, steady state response is also going to be a sinusoid at the same frequency. This is very important, at the same frequency, and just like a DC condition that V is scaled by the resistance, here the Vm, the peak amplitude voltage is going to be scaled by a term called as impedance, by a term which is called as impedance. Why impedance? Because it is impeding the flow of current, just like a resistance is resisting the flow of current when you close a voltage, apply a voltage to a resistor. Similarly, here the net effect of R, L and C, which is a impedance, is impeding the flow of current, hence a impedance, and the reciprocal of impedance is actually called as admittance, is also a sinusoid, is also a sinusoid. The current waveform is also a sinusoid scaled by the peak voltage amplitude being scaled by the impedance and shifted by an angle theta. So, every time we do not need to solve a integral differential equation, please. Now, we know what is the trick to be done if we are actually solving a series RLC circuit, and this is where I am actually motivating towards a phasor analysis. At some point of time I am going to say that we can drop even this sinusoids and we can just work with numbers. So, for that, for motivating this particular fact, I want you to, I would also like to solve a parallel RLC circuit, but before that let me just mention that impedance mod of Z has unit of ohms. Why? Because you, if you want to write mod of Z, you would take this thing here and take this thing down here. So, on the numerator you would have voltage, on the denominator you would have current, and anything which is ratio of voltage and current has a unit which is equivalently that of impedance or ohms. So, therefore, I can for example say that I have a impedance of 3 ohms at an angle of 30 degrees. This is good enough, this description is good enough. I need to specify, I need to specify this theta and this z, then the whole of this triangle is properly described, or I can give you individual components as I had given it, and the angle is of course dimensionless quantity. So, therefore, this whole thing for example I can say has something Z has an impedance of 3 plus 3 angle 30 degrees, and if something can be written like this, then this is actually a polar form representation of a complex number. I can also have a rectangular form representation of this complex number, and that would also suffice. How we will use that we will see later on. Suppose I decide to write it as 3 times of cos of 30 degrees plus j sin, I think I am jumping a lot, j plus I am going to use plus j times of sine of 30 degrees, where j is square root of minus 1. Now you must be thinking, why is, I mean all through our school we have used the notation I to be the square root of minus 1. Why suddenly in the, when writing a complex number in rectangular form, why I have used j instead of I? So reason is very simple. In electrical engineering, I is usually used to represent current. So then the same I cannot be used to represent the square root of minus 1. So what is the next alphabet in the alphabetical list? What is your next alphabet? It is the alphabet J. So therefore, in electrical engineering, usually a complex number is the square root of unity, the imaginary number is usually represented as under root of minus of 1. Now, I want to just demonstrate to you one more thing before one more thing, which is that when I add 2 sinusoids at same frequency, it is a sinusoid also at the same frequency, but with a different magnitude and angle. So towards this, first let me expand the first term, which is sin A plus B is sin A cos B plus cos A sin of B. So sin of omega t cos of this and cos of omega t cos of sin of phi 1. So sin A cos B plus cos A sin B, and similarly for the second term B of, I can write this as cos of phi 2 plus B times of cos of omega t cos of phi 2, and now if I add these two things together, it will turn out to be A cos phi 1 plus B cos phi 2 into sin of omega t plus A sin phi 1 plus B cos phi B cos of I am sorry B cos sin of phi 2 times cos of omega of t. So, now think of two vectors A at an angle phi 1 and B at an angle phi 2. Where are these two A vector and B vector come from? The A vector has come from A, that means this sinusoid I am trying to represent it as by a vector with magnitude A and angle phi 1, and this one, I am sorry, this should have been a sign here, and this other one I am trying to represent it as a vector B of magnitude B and angle phi 2, omega being same across both the sinusoids. I am not using it. If I now write these two vectors and if I project it along the if I project it along the x axis, what is this component? This component is B cos phi 2, and what is this component? From A cos of phi 2, and what have I got here? So, basically I have summed the two x components together. Similarly, here on the y axis, I have summed up the projection of this, this and this projection. So, this is B sin of phi 1 and this is A cos of A sin of phi, B sin of phi 2 and A sin of phi 1. So, these two are being added here. So, when this is the way it is being done, the resultant which is if I look at the, so it's now it's getting clear to you that basically I am adding two vectors. It is like saying that this is vector A, let us say, and this is, let us say, vector B, and what I have done is a vectorial addition of it, which is C. If I represent it the same operation in this way, then you will automatically see that if this is what is done, then the x component of A vector plus x component of B vector will get added here, which is the term which is coming out here, and similarly the y projection of A vector plus the y projection of the B vector are added, and this is A cos phi 1 plus B cos phi 2, and this is exactly equal to A sin phi 1 plus B sin of phi 2, and now the modulus of this C vector is nothing but equal to sum of plus B cos phi 2 whole square plus A sin phi 1 plus b sin phi 2 whole of square, and this can be written as a square cos square phi 1 plus phi 1 plus a square cos square b square cos square phi 1 plus the term coming from here b square sin square b square phi 2 plus sin square phi 2. So now I have, this is when I do a plus b whole square, it is a square plus b square plus 2ab plus 2ab. So the third term will be 2ab cos of phi 1 cos of phi 2, and when I look at the 2ab term from here, it is going to be 2 times 2ab, which is taken out as common, plus 2 times ab times sin of phi 1 plus sin of phi 2, which is same as now cos square theta plus sin square theta being 1, this is a square plus b square plus 2ab cos of phi 1 minus phi 2, which is mod of c square. And if this angle is some angle phi, then it is the ratio of tan of phi will be ratio of this y component by the ratio of this x component. So therefore tan of phi will be a1 a sin phi 1 plus b sin phi 2, this is this one a sin phi 1 plus b sin phi 2 divided by the x component, which is a cos phi 1 plus b cos of phi 2. So what is this? This is nothing but the parallelogram law of identity. Okay. Now let us come back to how we are going to use this. So this I am going to, whatever is this c vector, I am going to divide this by this mod of c, I am going to divide this by this mod of c, and I am going to multiply this by this mod of c, and then I am going to do the same thing here. So as to keep my life simpler, I am going to reuse this space. Then what I am going to do is I am going to write this as mod of c. Now this I can write it as cos of phi sin of omega t, plus I can write this as sin of phi times cos of omega t, and so I can write it as this as sin of omega t plus phi. So what is the conclusion that I have come to? Actually I have come to this conclusion that this is right. I can actually write summation of two sinusoids at same frequency. When I sum them together, it is also a sinusoid at the same frequency, but with a different amplitude and a different phase angle. And to calculate that, I need not do this trigonometric simplification all the time. What I can do is, first sinusoid I will show it in a vector form, second sinusoid I will show in its own vector form. I will do then a parallelogram law of identity and get the resultant vector c at an angle phi. Once I have got the resultant vector c, I can then just so what I have done, I have taken one vector like this, I have taken another vector like this, and I have just calculated this C at an angle phi. Just I have done a vector addition, that is all I have done. A vector plus B vector equal to this C vector, that is all I have done, and I have got the magnitude and angle of it. Once I got this, then I will say okay, my resultant summation is C times sine of omega t plus phi. Suppose cosine was taken as a reference, everything I am working every time taking sine of omega t as the reference waveform. If you had started all this algebra from cosine of omega t as a reference waveform, then you would have come to the conclusion that this is nothing but cos of omega t plus phi. This is with sine of omega t as a reference. This is the same, this is the conclusion you will derive if you take this as reference. So, this A of phi, see for example, if you are in our series RLC circuit, we are summing the voltages across the VR, VL and VC, we are summing the three together, they are all at the same frequency. So, you could actually do the addition and it is a new voltage waveform at the same frequency. In fact, we did it brute force at the beginning, and this is what can be, this is how we motivate the notion of phasor. Instead of dealing every time with the time domain waveform, writing everything as sine omega t plus phi, cos omega t plus phi, and then all trigonometric additions, much better to take these sinusoids, but important thing is they have to be at same frequency. This is very important. Convert them into vectors, and for vectors later on already you know that you can use complex numbers also instead of vectors. We will have more of it later in the later classes. So, convert it into vectors which are called as phasors. Do your addition subtraction manipulations here in the vector form and then get it back here, and if you want express it as, so you took sinusoids and converted them into this form and you got A plus B into this form, and now once you have got this C, you can re-express it in time domain if you want to do. So, therefore, phasors basically take away that unnecessary complication of the term called time dimension, and they are able to do that because we are dealing only with sinusoids in our steady state, and all those steady states, all those sinusoids are again at the same frequency. So, therefore, adding or subtracting sinusoids at the same frequency creates a new sinusoid at the same frequency. This is the basic fact that we are trying to exploit. Now, if somebody says, can I do this with phasors? Answer is a big no. Why? Because one frequency, one sine of t means omega is 1 radian per second, sine of 2t means omega is 2 radians per second. You can do this addition in time domain, there is no problem. Sine A plus sine B, you can do something about it, there is no problem about that. But the resultant waveform is not, there is no one common frequency. So, you can't say resulting waveform will be at sine t or resulting waveform will be at sine of 2t. So, for doing phasor analysis, all the sinusoids have to be at the same frequency. Now, suppose all of them are at same frequency. If somebody says, can I do the multiplication? Because they are, both of them are at the same frequency, then this is what, this is half of sine of 2 omega t. So, the resultant waveform is actually a sinusoidal waveform, but the frequency has doubled. So, again multiplication does not imply a phasor analysis, you know, it is only when the addition or subtraction that the vectors we can directly use the vector algebra. Here again it is not multiplying the two phasors at same phasors will not create a new phasor at the same frequency. This is something altogether, the frequency has changed to 2 omega. So, please be very careful about this phasor analysis. They can be done only in manipulating, that is adding and subtracting sinusoids at the same frequency, but even though with such a limited ability, a significant amount of electrical engineering gets done. Finally, what about sin omega t by cos of omega t? This is not even a sin or a cos, this is tan of omega t, and if you plot a tan of omega t, it is a entirely funny looking waveform going towards plus infinity here and going towards minus infinity here. It does not, at least if this was the sine of omega of t, sine of 2 omega t is just a double frequency waveform, but still looks like a sine. This waveform even does not look like a sine. So, the ratio of again ratio of two sines cannot be addressed at the same frequency, cannot be handled through algebraic manipulation of phasors. Multiplication of two sines at same frequency also cannot be handled by the method of phasors. Only addition and subtraction of sines usually can be handled through the at the same frequency can be handled through phasors. But that itself is a big thing. Why is it that a big thing? Because KCL, the Kirchhoff's current law, and KVL, the Kirchhoff's voltage law. What does Kirchhoff's current law say? Suppose I have these three ones, this is I1, this is I2 and this is I3. Then I know that I1 plus I2 is equal to I3. If these two are sinusoids at the same frequency, then I can directly take the phasor representation of I as a vector I1, get the phasor representation of I3 by adding these two phasors or the corresponding vectors, I can get this. So, the KCL can directly be can use phasors, that is the beauty of it, there is no problem. Similarly, if I go across a loop in a circuit, then the summation of the voltage rise is equal to the summation of the voltage drop, just like what we just like what we did with the series RLC circuit. Now, if summation, if each one of them are at the same frequency, so that means suppose I had connected in my RLC circuit, I had connected one voltage source, say 10 sine of omega t, and another voltage source, let us say 20 cos of omega t. I can do a phasor analysis because I can apply superposition and with 10 sin omega t find what is the response. I can apply this, find what is the response for the current. Both of them will be two phasors at the same frequency omega. I can superpose the phasors and get the answer, or I can superpose, I can write this as a phasor 10 and I can write this as a phasor phasor 20 cosine. I can write this as a phasor with an angle of 20 with 90 degrees. I can add these two phasors together, get the resultant voltage and then solve the RLC circuit. I can do all that. So, so phasor additions and subtractions translate very well with KCL and KVL, and that is why and all our voltage sources are going to be at 50 hertz basically. So, that is why we will be very comfortable with phasors and we will be using them throughout this course. We will be developing this concept more and more as we proceed forward. With this, I think I am going to stop this lecture. Thank you.